to describe the effect of changing pressure and changing temperature on solubility. That is, the ability of a solute to dissolve in a solvent. Before we discuss the effect of changing pressure and temperature, we have to understand the energetics of when a solute dissolves in a solvent. In this case, we are showing here a stepwise, somewhat unrealistic process. I say unrealistic because when a solute and a solvent mix, we want to make sure we understand the energetics associated to it. So we unrealistically separate them, so we have to break bonds among solute and solvent, so that will always involve some energy and some energetic cost. But what makes the solution viable is how much energy it's gained when you mix the separated solute and solvent. In any case, we will have an exothermic process if the energy, or the internal energy, the enthalpy of the solution is lower than the solute and the solvent. We will have an endothermic process when the solution in here appears to have more internal energy than the solute and solvent separately. Notice that when we mix the solute and solvent and we observe an increase of temperature, that will mean that that increase of temperature is because of the heat released when you mix, that will be this heat, the heat released when you mix solute and solvent and create the solution. When the process is endothermic, you will see a decrease of temperature. Okay, there is another magnitude other than enthalpy or internal energy that we need to understand, or at least mention, before we tackle the effect of pressure and temperature. And that is a magnitude called entropy. We do not have a lot of time to talk about it. There will be plenty of time to do so. But think of the entropy as the capacity to spread out. Nature has a capacity to spread out the particles. And so the processes in which the particles spread out, those will be favorable. Okay, so in other words, when the entropy increases, it means that the particles kind of spread out, and that's somewhat favorable. So we'll have to take that into account to explain why is it that pressure and temperature have a specific effect on solubility, depending on if the solute is gas or liquid. So let me give you an example of what I just said. It turns out that when we mix gas as solute, okay, so this is where the solute is a gas. When we mix a gas in the solvent, it turns out that the higher the temperature, the lower the solubility. And that's a very well-known phenomenon. It's called the thermal pollution. It's well known when the rivers or some areas where there's fish, and those rivers have an increased temperature of the water. Because of the increased temperature of the water, there is less oxygen dissolved in the water, and that kills a lot of aquatic populations. That's very well known. Also, your soda will be more bubbly, will appear more carbonated if it's warmer, because the CO2 is ready to get out of the solution. In this case, notice as we go from lower to higher temperatures, the solubility in all the cases will decrease. That may depend also on the kind of interactions between the solute and the solvent, but typically is well known, this factor. Now, why is it? The explanation is because of entropy, that variable that I just mentioned, the capacity of particles to spread out as you increase the temperature. So in this case, because if you picture a liquid solution with particles of gas trying to go into the liquid, there will be more constrained in the liquid, less spread out. And here in gas form, they'll be more spread out. They'll have more freedom, if you will. So this is why, as you increase the temperature, the so-called entropic effects, or the capacity for particles to spread out, will be larger. This is why, as you increase the temperature, the likelihood of the gas solute dissolved in the solvent will try to escape. Okay. Very different is when the solute is a solid. In this case, you will see in here, generally, and that strongly depends, but generally, as you increase the temperature, the solubility increases. Solubility. Um, oops, solubility. There you go. Increases. So as you can see, anything that goes with a positive slope, and it depends on the compound, but it's generally this trend. How can you explain that in terms of entropy? Well, if you think of a solute, solid solute, they are all constrained in here. When mixed in water, suddenly you have them all spread out. So in water, or dissolved in the solution, the solid is more spread out, and this is more favorable as you increase the temperature. Okay, so this is a little bit what it's trying to say, this text. Generally, it will, for solid liquid solutions, the higher the temperature, the higher it will be the solubility. There's some exceptions. Some exceptions, in this case, cerium sulfate is one of them, but in some cases, the ions, think of this as a cation, then an anion. Some ions really carry along a lot of waters, and that kind of constrains the motion of water, and it's not favorable. It's not favorable in the sense of this capacity for nature to spread out, because now suddenly these waters are not free to move, they are bound to the cations and anions. So in some hard ions, some ions that have the capacity to surround themselves with a lot of waters or very firmly, this trend will be the opposite. Don't worry, we will not ask you to discern between which one is which, but just so you know, because you may see some exceptions in those cases. So that was the effect of temperature. The effect of pressure may be more intuitive. The idea that the higher the pressure, the more you're forcing the gas into the liquid, therefore the higher the solubility. Solubility, okay. And a very daily experience, a very common daily experience is when you open a bottle of soda. When you open it, you'll hear the noise of molecules of CO2 escaping the solution. It's because when you open the bottle, the pressure diminishes, therefore the solubility decreases, and you see solutes escaping. Notice that we will not do the case of the effect of pressure when solute is a solid. Solute is solid. We will not do this one because it's barely the effect of pressure in this case is not very remarkable. Okay, so we are ready to just run a simple question. In this case, it's asking for the case of a solution that has potassium chloride, which again it's an ionic compound, therefore it's a solid at room temperature, and CO2, carbon dioxide, it's a gas, as you well know. Okay, and we say that the solution is heated near boiling. So what is it going to happen? Well, we know that as you increase the temperature, typically when the solute is gas, the solubility will decrease. However, when the solute is solid, the solubility will increase. Therefore, when the solid is a gas, this is the case of CO2, and the solute is solid, this is the case of potassium chloride. So when you increase the temperature, expect the CO2 to leave the solution and the potassium chloride to get more dissolved. So A, precipitate means that it leaves the solution. Well, that's not true because it's going to increase. Some CO2 bubbles out of solution. Well, yes, this is what we said it's going to happen. Some CO2 bubbles out of solution and some potassium chloride precipitates. No, this is not going to happen. Okay, so of course you're not going to see more potassium chloride dissolved because it's already dissolved. So what you're going to observe is some carbon dioxide leaving or bubbling out the solution.